and this is the first time I've spoken about this publicly. I had what I believe to be an encounter late at night, and my wife was next to me, sleeping, and it occurred over the course of 3 days. I'm going to actually just start the video, and we're going to actually watch the video. This is the video. I'm going to stop it, and we're going to go back to other parts of it. Pressure is essentially zero in space, and objects act very differently with zero pressure than they do with the 14.7 pounds per square inch that we live under. Now, you can show this on Earth. If you fill a cup with water and you put it inside of a chamber and you evacuate all the air, the water will boil. It's the same boiling that you get when you raise it to 212 degrees Fahrenheit sitting on your stove. But when you take the air away, the water will boil. It's because boiling is a function of pressure. And in zero pressure, it'll boil immediately. So up in space, you can have some very strange effects happen, especially because in your experience, you're not used to seeing zero pressure, you know, and you're not used to experiencing objects that operate in zero gravity. You don't recognize the croquet ball effect and how effective it is. Two tiny particles coming together can bounce off each other in a perfect right angle. Or, as we'll see here, the objects look like they're making strange maneuvers when in fact it's all very explainable if you know how things work in space. When a spacecraft heads into space, it has a liberal coating of ice on it already because of the fuel used, the liquid cooling. It's very, very cold. You can look at the shuttle and see that it's covered with ice much of the time. Many times on the external fuel tank and on other places, it's covered with ice. That ice persists. You would think it wouldn't, but it does. And when they, on Earth, there's, the ice would melt if it was left on the pad and the tank was emptied out. But that stuff is so cold in the tank that it's a continual refresh of ice. The shuttle's engines are using it. There's ice forming inside the shuttle. It gets out. It floats around. There's debris. And it's as nasty as it sounds. On orbit, the shuttle is surrounded by a debris cloud. So is the ISS space station, so is every single spacecraft that's ever gone into space. It's surrounded by a debris cloud. Why is that? Because as it gets into space in zero gravity, once you're in orbit, there's nothing to blow the stuff away. If it falls off, it just sits there and surrounds it and stays there. All right? And that's what we saw here. Let's play it again, Sam. So, now, in space, what happens to ice is, you would think, well, geez, in the bright sunlight, it should just evaporate immediately. No, it's not how it works, because on Earth, we have air around objects. And when you have air around objects, air has a value of warmth to it, it has temperature, and that serves to melt ice that it surrounds. You've seen it. You put an ice cube on a table, you get a puddle, and the ice is rounded all around it. It has that nice sheen to it. That's because the warm air is melting the ice. In space, there's no such thing. A craggy piece of ice will remain a craggy piece of ice floating around. Why doesn't it melt from that much more intensely bright sunlight? All right, it doesn't melt because ice is very bright. And all that you have in space is the ability of an object to absorb solar radiation and retain it. Well, ice is very reflective, so ice doesn't do that. All right? And when it does absorb what little it does absorb, it takes that ice and it goes immediately to a gas, okay, well, water vapor. It doesn't go to water first. That process is called sublimation. On Earth, you know that very well with dry ice, which is carbon dioxide gas frozen, right? You take a hammer and you press it down. Just press it, don't hit, but press it down on that dry ice. That hammer is so much warmer than the ice that as you press it down, that dry ice starts to sizzle and pop and go zzz, and it vibrates your hand. It's a lot of fun. Well, truthfully, when you do that, on Earth, you can recognize that. But in space, water ice does kind of the same thing. Any solar radiation that does get into the ice tends to sublimate a little bit of the ice away to water vapor, which floats away. But you got to also understand that ice is also full of trapped air. And so in space, when the solar radiation is absorbed enough to allow some of the ice to sublimate away, maybe an exposed pocket of air is exposed, okay, and it acts like a little jet. In zero pressure, it doesn't take much, and the thing goes and takes off. the reaction control thruster systems on the shuttle, when they fire, there's no bright explosions of fire every time they throw a thruster off in the shuttle. And as a matter of fact, in space, you see no fire per se. Thrusters look just like, if there's anything in the way, you'll just see movement of the object that's being pushed away. And that's what happens sometimes with particles that get blown away. Let's take a look at this now. I want to show you a particular example. These particles right here, when I looked at them, they look to me like out of focus particles in the near foreground. Why would I say that? Because, I'm going to pause it for 1 second. See this object right here? Let's go back and just watch that one more time. And I want to see it come down. You see as it comes down how it looks like it's blinking? That's because it's a piece that's rotating. And it's catching the light, shielding the light, catching the light, shielding the light as it rotates. But because it's vastly out of focus, it just looks like a singular round thing. Now you say, well, how can it look like a singular round thing? I'll show you why. I'm just going to minimize this for 1 second. This is a telescope. It's called a Schmidt-Cassegrain. It has a main mirror down at the bottom here, which you can see, and it has this round thing here. It's called a secondary mirror. Light comes in here. This is like a glass plate called a corrector plate. The light comes down, hits this mirror, bounces up to this second mirror, goes down through the hole in the main mirror, and out the eyepiece, or to the camera. On the shuttle, they don't have room for big, long telescopes. They need telescopes that fold the optical path like these do. So they have this design, or what are called Maksutov designs, which look very similar. And these have this obstruction. They call it a secondary obstruction. Now, in the video that we just saw, okay, when we go back and look at some of this video, you'll notice that every one of these highly out of focus objects, like this one right here, see the round holes? Yeah, that's what it looks like. But see, what's the proof? The proof is the image I'm about to show you. That's an out-of-focus image taken in a telescope that's a Schmidt-Cassegrain or Maksutov design. Highly out-of-focus image looks like this. There's the secondary obstruction. It shows up in the image. Now, the other thing in the tether video, one of the things that's interesting is when you look at it, you also see the strange notches, which are in the objects. All right, and this object right here is the one we want to focus on. Now, you see there's a notch at the bottom and a notch at the top, right? Watch the notches carefully. The notch at the bottom disappears and reappears at the top. Did you see that? Watch again. If you're not too dizzy. Watch that notch. It goes away, and then you see it appear at the top. See that? Here's what you're looking at. This is an out-of-focus object, piece of debris or a piece of ice. That tether broke, and tons of debris were left when this giant tether broke. It was over 12 kilometers long. And so what happens is you'll notice that this notch and that notch there, see how that notch vanished and here it is? See what it's doing? This notch is actually a video artifact of this long, thin, linear tether that's been superimposed on the out-of-focus objects. And when they zoom out later in the video, you see that those large, round objects disappear entirely and become, here we go, and become less focused but smaller objects. And now you can see that these are debris. You know it because if these were far, far away, when you zoomed in, okay, they would be big, and when you zoomed out, they would still be big. And they're not. They're now tiny. And that illustrates right there that they are in the extreme foreground, right outside the window. So, this all said, I think it's fascinating to view these types of videos and to try and explain using an understanding of an environment that it's totally foreign to us, and we are probably never going to see. And that's the zero-gravity, micropressure environment of Earth orbit. But these things have been following ships and spacecraft around ever since they've been launched, because we're bringing a whole bunch of crap up to orbit with us. And people need to understand that. And you need to temper your investigations or your thought processes with that information. Now, I'm a skeptic, but not about UFOs, not about the fact that they're here. You'll see why in a moment. But I'm a skeptic about data.